So now we can represent triangles on the screen, which is great. But if you haven't noticed, things on the screen can move. And to make these things move, we'll need to apply what we already know of linear algebra and matrix transformations. But first, we need to understand what a world coordinate is and a local coordinate is. Now this example is in 2 dimensions, but world and local coordinate systems exist in any number of directions. So here we have a basic billboard. On this billboard, we'll define a coordinate system. And with this coordinate system, we can define the locations of points. So here are 3 points that are on our billboard. Now these are all correct points. Now let's say we want to use our billboard. So we put up some forms. These points are also all on top of forms. But just with the location of the points, we don't know where they are on the forms. And this is where our local coordinate systems comes in. Basically, we'll have to set up another coordinate system for every form. And these points will have a value in the world coordinate system, and they'll also have a value in the local coordinate system. Now the local coordinate system is much more useful because you don't really care where the point is relative to the entire billboard, but you do care where the point is relative to a single sheet of paper. This means that every point now has 2 coordinates, one that's defined in the world and one that's defined locally. Now it's important to note, how did we get these new coordinate systems? What we actually did was apply a translation on all of them, but we didn't apply a translation on the points. We applied a translation on the actual coordinate systems themselves. This is important because objects defined in 3D, the vertices that define those objects aren't defined in the world view, they're defined in the local view. So every object will usually have its own local coordinate system. And the points that define the object will be defined in the local system. And a great way to think of these local and world coordinate systems is to think of them as vector spaces. So we don't only have to apply translations to the world coordinate system to get the local ones. We can apply a scale, rotation, we can squash them a little bit so the basis vectors are completely different. We could apply a reflection to it. And basically what this does is that every local system will have its own set of rules that won't affect the 3D space as a whole. It'll only affect its object. Now on to the actual transformations. Since we're working in Euclidean space, we'll be able to do at least all of the Euclidean transformations. So the first and simplest one is translation. Now all matrix transformations will have approximately the same form, so I'll explain what every variable means here. P prime will basically be the location of the vertex after the transformation is done. And then you see a 4x4 matrix. Transformation matrices have to be 4x4 because the points are all in homogeneous coordinates. And the reason they're in homogeneous coordinates will be explained later. But for now, for every Euclidean transformation, the bottom row of the matrix is 0, 0, 0, 1. And the 4th variable for the point is also always 1. So it's not going to affect the actual 3-dimensional location of the point. Now for translation, the Vx, Vy, and Vz will be the direction and amplitude of the translation. So you could go +1 in Vx, that means it's going to move 1 unit to the right, or -1, it's going to move 1 unit to the left. And that's the same for Vy and Vz. And for the point, Px, Py, and Pz is the original location of your point. Let's say I apply a translation to this square on the screen. We can see that this square is at position 4 on the x-axis and 7 on the y-axis, and at 0 on the z-axis since there's no depth in this example. Now let's say we want to move it 14 units to the right. That means that our translation matrix in Vx will replace it with 14, and Vy will replace it with 0, and Vz also with 0. And as you can see, if we apply the matrix multiplication, P prime will be equal to the same point mathematically as it is on screen. The next Euclidean transformation we have is scale. And here, Vx, Vy, and Vz will be the amount of times you want to make the object bigger on that axis. So Vx will be the amount of times we want to make the width of the object bigger. Vy will be the amount of times we want to make the height of the object bigger. And Vz will be the depth. So if you replace all of those variables with 2, it's going to be 2 times as large, 2 times as high, and 2 times as deep. So let's see this in action. Let's say we want to make this square 4.5 times bigger on the x and y axis, and 1 time as big on the z-axis. Now if you don't want to scale an object on a particular axis, it's important not to put 0 there, because that means your object is going to be completely flat. You want to put 1, so it's 1 times as large as it was before. Now unlike the translation, a scaling transformation won't affect every vertex in the same way. In a translation, every point in the object will be moved in the same direction for the same magnitude. But here, the top right corner of the square and the top left corner of the square won't be moved in the same direction at all. One is going to go to the top right and one's going to go to the top left. And this is where our local coordinates come in handy. We're going to define a local coordinate system in the middle of this square. And we're going to observe the movement of the top left square. So that means that the top left point of the square is at minus 0.5 to the left and plus 0.5 up. So it's going to be at minus 0.5 plus 0.5 in the x and y coordinate. And if we apply the matrix multiplication that I just described to you, it'll give us that the final position of our point will be at minus 2.25 on the x-axis and plus 2.25 on the y-axis. And that's exactly what we can observe on the screen. For rotation, we have 3 different matrices for the 3 different angles on which you can rotate an object. Now, as you can see on these matrices, the column and row that will see no change with the matrix multiplication is the one where the axis is getting rotated on. So if you rotate on the x-axis, every point on the x-axis doesn't actually change position. Now in our example, since we could actually see a rotation on the x and y axis, we'll have this rotation go through the z axis. So we're going to use the transformation matrix that's associated with rotation on the z axis, and this one. So let's say we want to rotate our object 45 degrees. In computer graphics, everything happens counterclockwise. So if we put in 45 for theta in our z rotation axis, in our matrix multiplication, we'll get as a result minus 3.2001. And since we were observing the top left corner, we can see that now it's actually parallel to the center of the square. That means it's not going to have a y value anymore. And it's completely to the left of the center of the square, which is why the x value is negative. So we've done every Euclidean transformation, but we still haven't used that homogeneous coordinate. That's because the homogeneous coordinate is not used for Euclidean transformation. Our last transformation, and the one that's probably most important out of all of them, is the perspective transformation. And that is defined by this matrix here. Now, here we actually use the w coordinate. And this is to make our objects grow from an orthographic projection to a perspective projection. So I've said this before, but a computer does not see like us. A computer will take a 3D environment and project it onto the screen. But it's not going to project it in the way that humans see, because we have a cone of vision. But a computer projects things orthographically. That means that every ray that comes from the environment will be projected at an angle of 90 degrees on the screen. That's why if we just present a cube on the screen, it's going to look like this. But if a human sees a cube, it's going to look like this. So we can change how a computer sees a 3D environment. So how we do this is we actually cheat our way through and simulate a perspective by physically changing the objects in the 3D environment. So when you see a box represented like this on the screen, even though it might seem like it's a perfect cube, the square that's in back is actually smaller than the square that's in the front. So this matrix is a little bit more complicated. So W and H are defined under it. FOV W and FOV H stand for field of view width and field of view height. That's the angle that you can see on either side of the screen from left to right and from top to bottom for W and H respectively. F is the difference between the user and the far clipping plane, and N is the difference between the user and the near clipping plane. Now this matrix transformation can actually give you a different value for PW than 1. And this value should always be 1 so that we properly display it in a 3D environment. That's why after the matrix transformation, we multiply the resulting vector, which is actually a point, by 1 on PW. Like that PW will be 1, and every other point will be its appropriate location in 3D space. So here's a scene with the perspective projection matrix. You can see that there's a cylinder moving from side to side, and a sphere that is behind a triangle moving from front to back. Now here's the same scene without that perspective projection matrix. You cannot tell that the cylinder is actually a cylinder. It might just be a rectangle. And also you don't even see the circle moving. And we say circle because we don't know it's actually a sphere. It might just be a circle. But we could see it's behind the triangle just because the triangle is actually covering part of that sphere. But we can't tell if the cylinder is in front, behind of the triangle, or in front or behind of the sphere. Another example is just a walk in the park. With the perspective matrix, everything looks normal. You can see the distances between trees, the ground close looks close, and whatever's further away looks further away. But the same scene, without that perspective matrix, everything seems very distorted. The trees, you don't know how far away they are from you. When you see hills, you don't know if they're right next to you or really, really far away. The only time you could actually get an idea of the depth is when you go past the tree and the tree starts disappearing. But the tree doesn't get any bigger when you get closer like you might expect it. It just starts disappearing. And the same thing with cliffs or little hills. You don't know if you're climbing up a hill or going down it. That means when you go further or back, you don't actually have an idea of where you are because nothing changes since it's an orthographic projection. And when you move from left to right, that you can actually see because parts on the right disappear and parts on the left appear. But overall, this makes for a really unsettling scenario for untrained eyes. And it's normal that it is unsettling because we're not used to see the world in an orthographic way. And that's why the perspective projection matrix is so important, and why this non-Euclidean transformation is absolutely necessary when representing 3D graphics.